All right, so what we're going to look at now are some properties associated with intermolecular forces. The first property that we're going to look at that can be explained in terms of values associated with intermolecular forces is surface tension. Surface tension is the resistance to an increase in your surface area. We see that this value is going to be greater with substances with more intermolecular forces or stronger intermolecular forces. So your polar molecules are more likely to have greater surface tensions than your nonpolar molecules. Your classic example that has been used to describe surface tension is adding the drops of water to a penny. The water drops kind of attract to one another. If soap had been put on top of the penny, that would disperse those water droplets. Soap is very nonpolar and not allow the surface tension to build up, while water having hydrogen bonds is very polar. The next one we're going to talk about is capillary action. Capillary action is how plants are able to get water up from to their leaves, from their stems. It is, or from the roots, excuse me. It is a spontaneous rising of a liquid up a narrow tube, and the way the liquid travels is due in part to those intermolecular forces. There can be cohesive forces or adhesive forces that are accounting for how that water travels, what type of meniscus it's able to make. When you have cohesive forces dominating, the intermolecular forces for the molecule are different that's traveling up compared to what it is traveling in its container. So an example would be mercury with glass. Mercury is very nonpolar, glass is very polar, and so the nonpolar mercury atoms draw closer to one another rather than being drawn towards the polar glass, and so they form what we call a convex meniscus, where the molecules basically point upwards as opposed to towards the sides of your container. Adhesive is what we see with water in glass, or even like an alcohol in glass in a thermometer. We have a concave meniscus in those types of situations because there is an attraction for these polar molecules in the container in which they have been placed. So since the polarities are similar, they are going to be drawn closer together, and so the water molecules point downwards as opposed to the mercury molecules, which point upwards when they are placed in a polar environment. We would expect the exact opposite for water and mercury if they were placed in a nonpolar container. Viscosity is the resistance to flow. This is why syrup takes forever and a day to pour. Molecules that have large IMFs are more likely to be viscous than those with small IMFs. Now, syrup is primarily nonpolar with maybe a little bit of polarity due to the sugar molecules, but the big reason why syrup is so viscous is due to the molecular size. There are lots of places for intermolecular forces to develop. That's going to be able to increase the viscosity of syrups and similar solutions. So the type of force is going to play a role, but you can have London dispersion forces play a pretty significant role if your molecule is quite large. Next up is vapor pressure. We saw with surface tension, we saw with viscosity that they both increased as the type or the strength of your intermolecular forces increased. Vapor pressure is going to do the opposite. Vapor pressure is the pressure of the gas that is present at equilibrium, and it is determined just by, like all the others, by the intermolecular forces that are present. It does increase with temperature, but what we see is that the volatile liquids have pretty high vapor pressures. They actually have weak intermolecular forces to overcome, which makes it easier for them to escape and to build up that pressure. Non-volatile liquids are not as readily able to escape the surface of a liquid because they have to overcome those stronger intermolecular forces, and they have much lower vapor pressures as a result. So this curve here, you've got a red line, a black line, and a blue line. Those are vapor pressures for diethyl ether, ethanol, and water. At those specific temperatures and at those pressures on the y-axis, these liquids are able to boil. If I look at a given temperature, I see that water has the lowest vapor pressure of the three, and diethyl ether has the greatest. So diethyl ether would have the weakest intermolecular forces to overcome, and that's going to enable its molecules to escape and to build up the pressure above that liquid. Water, however, has much stronger intermolecular forces to overcome. It is not as easily able to escape and become a gas, so its vapor pressure is much lower due to that strength in its intermolecular forces. So melting point and boiling point, they are going to go hand in hand with your intermolecular forces. Melting point is the process at which molecules are going to break loose from their lattice structure and change to a liquid. Remember, when you have these phase changes occurring, your temperature is constant. The vapor pressure of the solid is equal to the vapor pressure of the liquid when you reach your melting point. The enthalpy, or the heat of fusion, is the amount of energy that is needed per gram or per mole for this substance to change state. And that value is going to become greater with stronger or more significant amounts of intermolecular forces, because those have to be overcome. Along with breaking loose from that lattice, you need to break those connections so that they are able to separate a little bit more and turn into a liquid. Boiling is also taking place at a constant temperature. It is when your vapor pressure of your liquid is equal to the vapor pressure of the atmosphere surrounding it. The energy it takes to convert all of those liquid molecules to vapor molecules at that pressure is known as the heat or enthalpy of vaporization. And just like with solids to liquids, this is going to increase directly with your intermolecular forces, because you still have to overcome all those. So this phase diagram relates pressure and temperature to one another. You can kind of see that there's a Y-like shape to this particular diagram. Solid is always found on the left-hand side, liquid in the center, gas on the far right. Anywhere along the lines connecting those states are where phase changes can occur at those specific temperatures and pressures. You'll also notice at the end of the liquid gas line, there's a dot that indicates the critical point, the temperature above which your liquid can no longer exist. And then there's also a dot at the center of the Y-like shape, and that is known as the triple point. That is the temperature and pressure at which all three states of matter are in equilibrium. They are all present at the same time. So here you're going to get some characteristics. You're going to be given some different substances. You're going to be asked to identify which substance best matches up with the property given and provide some justification for your choice. So of these three substances, CCl4, CF4, and CBr4, these three are all nonpolar molecules. So London dispersion is the primary type of intermolecular force present in these molecules. But if I look at the differences, the F, the Cl, and the Br, I know that F is the smallest of these atoms and Br is the largest. And so because they're all nonpolar, it's that size that's going to determine which one has the higher boiling point, and it would be CBr4 because that contains a greater number of electrons and would be more easily polarizable than the other two. CF4 would have had the lowest boiling point. It would have had the fewest electrons that could have formed those instantaneous dipoles. Here we're looking at three substances and determining which of those has the smallest vapor pressure: CH3OCH3, CH3CH2OH, and CH3CH2CH3. So these are all roughly the same size. There needs to be a pretty significant difference in the amount of carbons for one to be have a greater number of forces impacting on your answer choices for something like this. So like if you had like 8 or 9 carbons, that might be something that you would have to consider. With that in mind, CH3CH2CH3 is just carbons and hydrogens bonded together, so that would be nonpolar and would only have London dispersion forces present holding those molecules to one another. With CH3OCH3 dimethyl ether, remember that oxygen is going to have, if you draw out its Lewis structure, it would have 2 lone electron pairs on that oxygen, which is going to make it be a polar molecule, and therefore it would have dipole-dipole forces, but it cannot have hydrogen bonding because the hydrogens are not bonded directly to the O, and that is what has to be in place for hydrogen bonding to occur. So of the two choices so far, CH3OCH3 would have had the smaller vapor pressure compared to propane, CH3CH2CH3. Ethanol, my other option, does have hydrogen bonding. It is definitely polar because of that OH group, the hydroxyl group present at the end of the molecule. And hydrogen bonding is going to have a more significant impact on this property than the dipole-dipole forces. So because of that, ethanol would have had the smallest vapor pressure. It had the strongest intermolecular forces holding it together. Propane, CH3CH2CH3, would have had the highest vapor pressure. It had the weakest intermolecular forces, the London dispersion forces present. Here we're looking at viscosity between H2s, Hf, and H2o2. All 3 of these molecules are polar. H2s has a bent structure with 2 lone electron pairs on the sulfur atom. Hf is a 2-atom molecule with the fluorine being much more electronegative than the hydrogen atom, but that would have hydrogen bonding available because the hydrogen is bonded directly to fluorine. H2O2 is also going to be polar, but it's going to have 2 places for hydrogen bonds to occur. The oxygens get bonded to one another, and each oxygen is bonded to a hydrogen. So because there are 2 locations for hydrogen bonding as opposed to 1 with HF, the one with the greatest viscosity would be H2O2, and the one with the weakest viscosity would be H2S. Here we're looking at enthalpy of fusion. We want to know which of these has the smallest enthalpy of fusion. You have a molecular solid, I2, and then you have 2 ionic solids, CSBr and CaO. Well, I2 is nonpolar, so it just has London dispersion, while CSBr and CaO both are ionic compounds, so they have electrostatic forces. Your enthalpy of fusion is directly related to the strength of your intermolecular forces. So if we want the one with the smallest enthalpy of fusion, it would be I2. If we had wanted the one with the greatest enthalpy of fusion, I suspect it would have been CaO because CaO is a little smaller than CSBr, so it would hold those electrons more tightly and would require more energy to separate the calcium ions from the oxygen ions, but don't hold me to it.